All right, so today we're going to talk about geometry, and in particular, we're going to focus on projections for the next couple of sessions. What we're going to do today and going forward should look vaguely familiar from vector calculus, but we're going to illustrate these concepts using the language of linear algebra. So instead of dot products, we're going to use matrix multiplication, and instead of projection operators, we're going to use matrices and so forth. But again, a lot of the ideas should at least be the same. So let's just go ahead and dive in. So the first thing we need to know is that for a vector, we can describe its norm. This is just the length, or sometimes called the magnitude. These are just different words for the same thing. And you calculate the norm by taking the square root of the square of all the entries. And this works for any number of dimensions, not just two. So this is the Pythagorean theorem in disguise, but generalized to higher dimensions. So for example, if we take a vector, let's go ahead and take the vector, let's take v to be this vector, 1, 3, 5, minus 7, and 4. Right, we can compute the norm of v by just taking the square root of 1 squared plus 3 squared plus 5 squared plus negative 7 squared plus 4 squared. And if you add all these up, that ends up being the square root of 100, which is then just 10. So the length of this vector here, the length of this in 5-dimensional space is 10. So this may seem a little weird, but there's no reason why you can't have length. You can have length in 1 dimension. It's just how long you are on a line. You can have length in 2 dimensions. You can have length in 3 dimensions. You can have length in any number of dimensions. And the formula is the same idea. You're going to use the Pythagorean theorem. So this is just the Pythagorean theorem generalized. And this gives us an idea when you have a vector, how long is it? When you have some idea, not just adding them all up. This seems a little weird. Why not just add up the vectors or something? But it turns out that the square root of the squares turns out to be very natural in mathematics. It's one of these things that doesn't seem to be the right answer, but turns out is exactly what we need. And this works out in many, many situations. All right, another thing we can do with vectors, not just take their length, but we can take the dot product. So this is something you've been doing without realizing it. So the dot product, you would normally have done this. You would take the dot product, and it's just taking the first entries of 2 vectors and adding what you get when you multiply the second entries and so on. But one thing I want to point out is that this dot product is actually the same thing as taking one vector transpose times the other. So instead of the dot product, we're not going to use this anymore. We're just going to write it like this. And this is the same thing. So sure enough, if you take one vector, if you take a vector in the transpose, so that's going to be a row vector, this would be u, and you're going to multiply it by v, right? This vector is now 1 by n, and v is n by 1. And so what's going to come out is a 1 by 1 vector that's precisely this right here. So a dot product is really just matrix multiplication with vectors, where both the matrix and the vector are vectors. All right, so just a quick example with this one is we can take u and v, and here u is going to be the vector 1, 1, 1, 1, or 3, 2. And v is going to be the same thing as what it was before. 1, 3, 5, minus 7, and 4. And we can dot them. So this is just going to be 1 times 1. I mean, this is the same thing we've been doing with matrix multiplication, but now with just vectors. So this may seem a little weird, and that's okay. And here there's all these. What do we get here? We are going to get, we should get 20 when we're done. Let's see if that's what we get. So we get 1, 4, 9 minus 21 plus 8. So we get 9 minus 20 minus 21 plus 8. No, we actually get something else. We get plus 4. All right. So we get plus 4 there. So I did it wrong before, but that's plus 4 for that dot product. And one thing the dot product does that's really powerful both in linear algebra, but even more over statistics, is it kind of tells you what direction things are going in. So for example, let's just do a 2D example real quickly. If we take two vectors, let's go ahead and take 1, 1 and dot this with 1, 2. But we're going to write this. We're not going to write it like this anymore. We're going to write it like this. This is going to be 1, 1 transpose 1, 2. Right? This is just 1 times 1 plus 1 times 2, or 3. So this number doesn't really give us a whole lot as of yet. But keep in mind that if we draw this, if we graph these vectors, right? One vector here is going to be 1, 1, and one of these other vectors is 1, 2. Right? They kind of sort of go in the same direction. But on the flip side, if I take 1, 1, and I take 1 minus 2, we're going to get minus 1. And you'll notice the second vector right here, we take 1 minus 2. You'll notice that, in fact, the blue vector right here, the blue vector 1 minus 2, is kind of pointing away from this first vector, 1, 2. But that's a minus 2. Right? And in fact, if you look at the perpendicular, the blue vector is slightly behind the red perpendicular. So if you're asked the question, is the purple vector 1, 2 in the same, roughly the same direction as the red one, you would kind of say yes. And then for the blue vector 1 minus 2, is it pointing the same direction as 1, 1, the red vector? You would say, no, it's more no than yes. It's more pointing more away. And that the fact it's pointing more away is what makes this negative. And the fact that the first one is pointing more in the direction is making this positive. So we want to make this more formal. So how do we do that? Well, it turns out the dot product measures this very explicitly. This also works in higher dimensions too. So what we have is we can define the angle between two vectors, even in any dimensional space. So one thing is that if we take the dot product, or just the vector product between two vectors, this is going to be equal to the norm of u times the norm of v times the cosine of the angle between them. Right, so this cosine right here, this is always between -1 and 1. And so that can give us a measure. So if we solve for the cosine, we get that the cosine between two vectors, the angle between two vectors, the cosine is equal to this. And this is a measure between -1 and 1. In fact, in statistics, this is the correlation. So if you want to measure the correlation between two vectors, what do? You just take the dot product between them and divide by what's the maximum you could possibly get if things were perfectly aligned. And that gives you the correlation. And this gives you a measure between -1 and 1. And in fact, you can even find the angle between them by taking the cosine inverse, or the arc cosine of those two vectors, that whole thing. And keep in mind, the arc cosine is the same thing as the cosine inverse. So this gives us a way of measuring things. This works very well, even though we're now going to work in higher dimensions. It still works. So let's just do our running example. So we can find the angle. We can find the angle between these two vectors right here, between u and v from before. We can find the angle between them. So let's just do that. So first, I'm just going to find the cosine of the angle between them is equal to u transpose v over the norm of u and the norm of v. So we already computed this. This one from before is 4. That's what we did before right here. We already computed the norm of v. That was 10. That was from before too. And so the only thing that remains to do is compute the norm of u. So just remember u is equal to 11132. So the norm of u is equal to the square root of 1 squared plus 1 squared plus 1 squared plus 3 squared plus 2 squared. And if we add all those together, what do we get? We get square root of 16 or 4. So this is 4. So altogether, the cosine of the angle between them is 1/10. And so theta is going to be cosine inverse of 1/10. In general, the angle between them is not going to have a nice formula. There's no unit circle for these things. And in fact, that's why the correlation, why typically we measure just the cosine of theta and just give it a measure between -1 and 1, because especially in statistics, that's a much more natural thing. How correlated are these vectors? Well, in this case, they're kind of sort of in the same direction, but not really. And so keep in mind V in this case was 1, 3, 5, -7, and 4. And so if we kind of compare these two, vectors right here, right, we can kind of compare them slightly. Let's do it like that. Right, they're kind of in the same direction. They're all mostly positive, but that -7 really throws a damper into things and really makes it so they're not necessarily in the same direction. Okay, so that's angles and dot products. We're going to continue on this. So another thing we can do is we can project one vector onto another. And so that might look something like this. So we take one vector, say our vector u, and we might project it onto our vector v. Right, that projection is, we're just going to literally shine a light projection, and that has to be orthogonal. It doesn't matter where v is, it's just going to be orthogonal. And the projection is going to be this vector right here. That's the projection. It's literally the shadow. And so one nice thing about the projection is the projection of u onto v is always a multiple of v. Right, so the projection is just some multiple of the vector you're projecting onto, and the question is, how much of a projection is it? Right, so in this case, it's not quite all of v, it's only about 9/10 of it. And we want to figure out, okay, what is this orange vector on the v if we know u? So we want to figure that out. From calculus, you might have seen this formula. So there's this formula from vector calculus. This is a nice formula. This is the projection of v onto u onto v. So u is inside the function, so v is fixed. But I want to point out a couple things here. The first thing is that this bottom part here is in fact equal to the norm of v squared. So the dot product with itself is always going to give you the norm of v. To see this, why is that? Well, if we go back to the other definition of the dot product, keep in mind uv, that's just u dot v, right? The angle between a vector and itself is just 0. So this is if u and v are pointing in the same direction, or more explicitly, if they're the same vector, right? We can write v dot v or v transpose v as the norm of v times the norm of v times cosine of 0, but cosine of 0 is 1. So we just get the norm of v squared. So that's the v dot with itself is that. And perhaps another strange thing is we're going to write this top part. We're going to write that as u transpose v. Or sorry, we're going to write it differently. We're going to write it the other way around. So this is equal to, this part right here is equal to v dot u. So we're going to write this as v transpose u. And we're going to put this v over here too. Now, this is just a number. All this right here is just a number. So this is a vector. We can move it around. We're going to move it out in front. And we're going to kind of combine it. So we're going to get with v. We're going to put it in the numerator. V transpose u over the norm of v squared. And now this is going to be kind of different, but we're going to write it slightly differently. One more time. We're going to write it like this. And the reason I like writing it like this is because this is a function of u. V is fixed. Once you fix v, you want to ask, okay, how do I determine the projection of any vector onto v? And there's this. Now this may seem strange and new, but this is just a matrix. So v transpose, that's an n by 1 times a 1 by n matrix. So this is actually going to be an n by n matrix. And we're dividing all of this by some number, which happens to be that. So this is just a matrix. So this right here, this projection, this is really a matrix. And now to find the projection, all you do is you take a vector u and you just multiply it by that matrix. There's another thing that if we restrict, if you restricted v2 to be a norm 1, right? This is often called a unit vector. Then the projection of u onto v is just v transpose times u. So this is one reason why we're going to really care about whether or not vectors are unit vectors or not, because for example, if there's a projection matrix, the projection onto that vector is literally just this matrix. It's a vector transposed with itself, but in the opposite direction. It's not the dot product, it's the opposite direction. And it gives you a very nice way of writing down what a projection is. All right, the last thing I want to talk about is what we're going to do more in the future. But this is called perpendicular subspaces. Maybe let's go ahead. Let's go back. Let's do an example with this one. Let's just do an example. All right, so let's find the matrix associated with the projection onto V. So we have this V vector. And we want to find the matrix associated to that. Well, the nice thing is we can't quite use this formula right here because it's not a unit vector, but we can use this one. So this is the matrix associated to it. So that matrix, let's just copy that formula down right here. So the projection of U onto V is just V transpose over the norm of V squared times U. And the matrix is this part right here. That's the matrix. So we can actually figure out what that is. So this is going to be V transpose. So that's 1, 3, 5, minus 7, 4 times this vector. That's just a matrix. And then it's going to be divided by, we're going to take all of that and divide it by 10 squared. All right, so now this looks very daunting. Now it turns out when we do this, this turns out to be like a multiplication table. So this should just be a matrix where the ij entry is just I of the first one times j of the second one. So this should be 1, 3, 5, minus 7, 4. Then the next one will have 3, 9, 15, minus 21, 12, 5, 15. It just keeps going. All right, so it looks like that matrix, except we're going to divide it by 1/100th. So if you wanted to, you could actually divide all of them by 100. But now that's a single matrix. And so now the power of the single matrix is whenever we have any vector, not just the u that we wanted, but if we wanted to, we could calculate what's the projection of u onto v, where our u is the vector from before, 1, 1, 1, 3, 2. Right? All we do, this is just equal to this matrix right here times 1, 1, 1, 3, 2. So let's just do it. So it's going to be equal to m is 1/100th of this matrix times 1, 1, 1, 3, 2. All right, so now what do we get on the top? Let's see. So I get that one, and it's divided by 100. And so you may be thinking, okay, is it a coincidence that in fact you get the same thing as this column? Well, keep in mind the projection needs to be some multiple of v. This right here is v is the same thing as each column here is actually some multiple of v. So it's not a coincidence that we actually get a multiple of v. It is a coincidence that it happens to be one of the columns we just had. But it should be some multiple of v. So this is going to be you don't have to simplify this. This is kind of why our matrix algebra comes really nice into play. So you don't have to write all this out. But that's the vector that corresponds to, in this 5-dimensional space, u being projected onto v. All right, so let's just talk about one thing that we're going to do going forward, and that's perpendicular subspaces. So if we have a vector space, W, we can define W perp. This is the set of all vectors V such that V is perpendicular to all vectors for all vectors in the subspace. All right, so this is the set of all things that are perpendicular. So to give you a slight picture of what's going on here, right? If you had a subspace, suppose you had some plane. This might be W, that might be your plane in 3-dimensional space. Your W perp is going to be the set of all vectors perpendicular to that go through the origin. So that would be what W perp looks like. Now, this seems strange, but the perpendicular subspace is really just kind of a kernel. So the key idea is that if you have a basis, of W, then all you have to do is find the set of all things that are perpendicular to that. We haven't said what perpendicular means. At least it's clear geometrically, but perpendicular, so U and V are perpendicular if their dot product is 0. So these are the same thing. Perpendicular means the dot product is 0. So it turns out, W perp turns out to be a kernel of some matrix, which we all know how to find. So let's just do a quick example. So let's find if W is the span of two vectors. Like we want to find a basis for W perp. Right, so the step one is we have a basis. This is a basis for W. That's what span means, provided they're independent. So those two vectors are independent, so we know they're a basis for W. And so what we want to do is we want to find the set of vectors. We want to find the set of vectors in 3 space such that when you take the dot product with 2, 1, 3, you get 0. And when you take that product with 1 minus 1, 1, you get 0. So these both translate into equations. This one translates into x plus 2y plus 3z equals 0. And the second one's going to translate for x minus y plus z equals 0. And this is a set of equations that we know how to solve, right? And the set of x, y, z that solve this are going to give us vectors that are perpendicular to the two things that we want, which will give us a basis for W perp. All right, so let's solve this. We're going to use an augmented matrix. We're going to row reduce very quickly. There's a pivot. We have another pivot right here. There's a minus 1/3 rather. And then finally, we're going to make this one a 0 right here. Okay, so what's really nice about this is that we have our 2 pivots, but we also have 1 free variable, so we can solve this equation. So the set of all x, y, and z, well, z is free. X is going to be minus 5/3 z, and y is 2/3 z. So this is going to be minus 5/3 z, 2/3 z, and 1z, which we can write like this, with just a single vector times z. And now this corresponds, this is a basis. This forms a line. This traces out a line in 3-dimensional space, which is perpendicular. The set of all points that are perpendicular to both of these vectors is a line generated like this. And to see that this is correct, or at least intuitively correct, has the right dimensions, we can take this picture. We had a span of 2 things. We had a plane, and what we found was the line that's in fact perpendicular to it. So in fact, finding the perpendicular space, despite the fact that it has a new name, is the same thing as just solving a system of equations and finding the kernel of a very specific matrix generated by just taking the dot product with the 2 vectors.